Before electronic calculators were widely available, slide rules were frequently used to quickly estimate many different mathematical operations. Slide rules came in various shapes and sizes. But how do they work? Before we perform some calculations, let's look at the parts of a slide rule. There is the body and the slide. Each slide rule has several scales, marking divisions used for calculations. We will only be looking at the C and D scales today. There is also a cursor that is helpful for some calculations, which we won't be using either. Now we need to know how to read the scales. The C and D scales have primary markings of 1, 2, 3, 4, 5, 6, 7, 8, 9, and another 1 on the right. There is a larger division between 2 and 3, so that would be 2.5. There are 4 slightly shorter lines creating 5 divisions between 2 and 2.5, so those represent 1/10 increments. Likewise, the smallest lines here represent 2/100ths, so this point here would be 2.18. Depending on the length of the slide rule, there may be more or less divisions. This slide rule even has more room for extra labels between 1 and 2. The smallest divisions here represent 1/100th. For example, this would be 1.64. Now we are armed with enough information to perform our first calculations. Check out what happens when we slide the leftmost 1 on the C scale to line up with the 2 on the D scale. Directly across from the 2 on the C scale is a 4 on the D scale. 3 matches up with 6. 4 matches up with 8. Everything is doubled. Even fractional values work. 2.5 matches up with 5. What happens if we move the 1 on the C scale to 3 on the D scale? Now values have tripled. Let's try multiplying two arbitrary numbers, 2.6 times 3.5. First, line up the start of the C scale with 2.6 on the D scale. Now we see where 3.5 on the C scale lines up on the D scale. It appears to be right around 9.1, which is the correct answer. We were pretty close to running off the end of the D scale. What would happen then? Let's multiply 4.4 times 3.1. We move the start of the C scale to 4.4 on the D scale. 3.1 on the C scale is now off the end of the D scale. Instead, we can move the end of the C scale to 4.4 on the D scale. Now it looks like 3.1 lines up roughly halfway between 1.36 and 1.37. Let's say 1.365. We were expecting a result slightly larger than 10. Since we wrapped around the scale, we must move the decimal place once, giving us approximately 13.65. We are close to the correct answer of 13.64. That's all great, but how do we multiply numbers greater than 10 or less than 1? We can use the same trick of moving decimal places before and after the calculations. Let's multiply 1,240 by 37. For 1,240, we can move the decimal place 3 places to the left to give us 1.24 times 10 to the third. Likewise, 37 is 3.7 times 10 to the 1. Now we can multiply 1.24 by 3.7, and when we're done, we just move the decimal place back a total of 4 places. Looking at the slide rule, we have just less than 4.6. If we move the decimal place back 4 places, we have an estimate of just under 46,000. The actual answer is 45,880. To touch on division, we can reverse the multiplication process. For example, let's calculate 6 divided by 2. First, line up the 2 on the C scale with 6 on the D scale. Now we look at the start of the C scale and see that it lines up with 3 on the D scale. So why does this work? What is the magic behind the C and D scales? The answer is logarithms. We won't get too deep into what logarithms are, but there is one special property we care about, namely log of x plus log of y is equal to log of x times y. Let's take a number line from 0 to 1. If we take the log base 10 of 1 to 10, we get these values. Now you can see that the slide rule is just adding two logarithms by placing them side by side, giving us a quick way to estimate multiplication. log of x minus log of y is equal to log of x divided by y, giving us a method for estimating divisions. Many slide rules have other scales for performing various operations, such as trigonometric functions and raising numbers to powers. Though slide rules have become mostly obsolete, they provide an interesting glimpse into the history of computation.